Howdy, howdy, this is Mr. Potter. In today's video, we're actually going to be talking quite a bit about the absolute value function. This is one of our parent functions, but it is a rather special function. It behaves a little differently than a lot of the functions we're used to. So I want to talk a little bit about it. First, I want to talk about how we actually define it. Keep in mind that from a verbal standpoint, the absolute value function represents the horizontal distance from the y-axis. In other words, where x equals 0. So when I talk about the absolute value of 3, well, 3 is 3 units to the right. So it's 3 units away. If I talk about the absolute value of -4, it's 4 units to the left, so it's 4 units away. So that's one way to think about it, is that we can think about it from a verbal standpoint. It's really the distance from x equals 0, the distance from the y-axis. Another way that we can think of it is we can think of the absolute value function being a piecewise defined function. We could say it's defined as x for x less than or equal to 0, and the opposite of x for x less than 0. Because from what I know of the graph, I know that for values of x that are positive, we end up having a positive slope. But for values of x that are negative, we end up having a negative slope. So this is our traditional graph that we're used to seeing for the absolute value function. There is a third way to think of this. We can think of the absolute value function as being the square root of x squared. This is a nice way of thinking about it because it allows us to have the domain being all real numbers from -infinity to infinity, because squaring any number makes it either positive or 0. And then I can take the square root, so our range is still from 0 to infinity. So this is what we're expecting from our domain and our range. And of course, normally the square root of x squared would give us just x, but if x is negative, that kind of gets rid of the sign for us. So it really does lead back to this piecewise definition, which you'll actually find that in your calculus class, you'll actually be using this definition a lot more often than you'll be using the piecewise definition. But all three of these are good ways to think about the absolute value function, because they all encompass this idea that there's really two different types of situations. One situation when what's inside the absolute value is positive, and another situation where what's inside the absolute value is negative. So the other thing that we need to really understand about this is that I can do all of the transformations that we talked about in the previous videos to this absolute value function. So when I have something like the absolute value, so I have a times the absolute value of b times the expression x minus h plus k, what I'm really saying is that we're dilating horizontally by a factor of b, excuse me. Then translating horizontally by h units. Then we're dilating vertically by a factor of a. Then translating vertically k units. And remember, we talked about in our previous video how this is the order that we really need to think about it. We're doing a horizontal dilation, then a horizontal translation first, then we do our vertical dilation and vertical translation afterwards. So let's do an example of this. So I've got this expression. I've got f of x equals 2 times the absolute value of 3x minus 9 plus 4. And so when we're dealing with a problem like this, our first step is to identify a, b, h, and v, and also identify what these mean. So I know that a is 2 because a is always the coefficient in front of my expression. B is the coefficient of x, so b in this case is 3. H is the hardest one to figure out because remember that it has to be b times expression x minus h. So h in this question is positive 3, and v is 4. So what does this mean? This means that we have a translation 3 units to the right, and we have a translation 4 units up. Here, because a equals 2, we're having a stretch vertically. And because b equals 3, we're going to have a shrink horizontally. So all 4 of these things have to happen in order for us to graph this function. Keep in mind that we're starting with the traditional absolute value function. So I'm going to put the graph here, and as we did before, I'm also going to label a few of these characteristic points so I can see what's happening. So I know the absolute value function goes through 0, 0. I know it goes through the point 1, 1, and I know it goes through the point negative 1, 1. So the first thing that I need to do is I need to take care of this horizontal translation. I'm going to be shrinking by a factor of 3, which means all of these points are going to be moving inwards by a factor of 3. So 0, 0 is still going to be the same point, but this point, instead of being 1, 1, is actually going to be 1/3 1. And this point's going to be negative 1/3 1. And also notice that we also remarked about before that when I do a horizontal shrink, it looks a lot like a vertical stretch. In reality, what's happening is that my original graph, which was here and here, these points are being moved in towards the x-axis, towards the y-axis. So that's the shrink that we're talking about. Once I've done this, the next thing that I need to do is I need to translate this by 3 units. So remember, we have to do our horizontal translations after we do our horizontal dilation. So the next thing I need to do is move this over 3 units, which means my graph, which was here, now is going to get slid over 3 units. So my vertex is going to be at the point 3, 0. This part over here is actually going to be 3 1/3, or 10/3 1. And this point here is going to be at 8/3 1. And of course, it looks exactly the same as what we had. The only difference is that it's been moved over from where it was centered about the y-axis. It's been slid over. And then, of course, the next thing I need to do is I need to dilate it vertically, our vertical stretch, by a factor of 2, which means that my y-coordinates are going to end up being doubled. So that means instead of my y-coordinates being at 1, my y-coordinates are going to be at 2 for these 2 apex parts. My vertex is still going to be at the point 3, 0. But this point that was at 1 is now up here at 2. So it's 10/3, 2. Similarly, this is going to be at 8/3, 2. And so my absolute value actually looks a lot more stretched out. It's actually going to hit, ooh, I drew that horribly. Let me redraw that just a little bit better. So it should be at 10/3 2, so about a third of the way right there, and then another third of the way, 2 more up, and then another third of the way, 2 more up. And similarly, a third of the way, a third of the way, and a third of the way. So notice that this wide absolute value, if I could actually hit those points, this wide absolute value should look very narrow compared to the yellow absolute value. In reality, it's the yellow absolute value that's just been stretched up vertically. So notice that these points have all been moved up. Finally, the last thing that we need to do is we need to translate this graph vertically 4 units, which means that my points are going to go up on their y-coordinate by 4 units. So 3, 0 is actually going to be the point 3, 4. And this is the corner. This point up here is going to be 10 thirds and 6, and the point 8 thirds, 6. And again, it's not so much how my graph looks, although you should try, can't draw today. You should try and make it look as much as you can like the function that you're trying to graph. I can't draw a straight line. The idea, though, is that if I label these points, how they've transformed as they go through these transformations, that's going to make it a lot easier to understand what my graph should look like. Keep in mind that these are just sketches. Cool. So now the next thing I want to talk about is what is the solution to an absolute value expression look like? And there really are 3 different scenarios that we're going to be dealing with. One is our most typical scenario, and we're used to our parent function lying on the x-axis. And because it lies on the x-axis, this is what it looks like when it has one solution. Essentially, the vertex lies on the x-axis. But because we have these vertical translations, I could move my absolute value up. And moving my absolute value up gives me no solution. Similarly, if I were to take this absolute value graph and move it down, I could end up with 2 solutions, here and here. So just realize that when we have an absolute value expression and we're trying to find solutions to an absolute value expression, we're going to have a situation where we could have 1 solution or no solutions or 2 solutions. When we're talking about solutions, I can have a situation where the absolute value equals 0, which is going to give us the 1 solution scenario. I could have where the absolute value of something is less than 0. And keep in mind that absolute value is never less than 0, so that's going to give us a no solution. And I could have a situation where the absolute value of something is greater than 0, and that's going to give us the situation where we have 2 solutions. So that's really what we're looking for. The idea is that if I have the absolute value of something is equal to k, then I want to know when that expression is equal to k, or when that expression, whatever my argument is inside the absolute value, equals negative k. And that's really the technique that we're going to use for our next 3 examples. So I'm going to start with a very simple one. I've got 2 times the absolute value of x minus 3 plus 1 equals 2. And so I want to solve for this, and I'm going to solve for it exactly as I would if this was the variable that I'm trying to solve for. I'm going to subtract 1 from both sides, get 2 times the absolute value of x minus 3 equals 1. Then I'm going to divide both sides by 2, so x minus 3 equals 1/2. And looking at this, I've got the absolute value is equal to something that's bigger than 0, so I'm going to end up with 2 solutions. One where x minus 3 equals my 1/2, or one where x minus 3 equals the opposite of 1/2. And so what I end up here, when I add 3 to 1/2, I get 7/2. Or if I subtract 3 from a negative 1/2, if I add 3 to a negative 1/2, that's going to give me 5/2. So an example where I'm going to have no solution, let's say I've got something like 3 times the absolute value of x minus 2 plus 4 equals 2. And again, trying to isolate this absolute value as the expression, I'm going to subtract 4 from both sides, and I end up with 3 times the absolute value of x minus 2 equals negative 2, or the absolute value of x minus 2 equals negative 2/3. But keep in mind the absolute value of something must be greater than or equal to 0 it's never going to be a negative 2/3, so we have no solution. So the final example I want to do is a situation where I would have one unique solution. So if I have 4 times the absolute value of x plus 3 minus 2 equals negative 2, you can see what's going to happen here and where I can recognize the one solution situation pretty easy. I'm going to add 2 to both sides. I get 4 times the absolute value of x plus 3 equals 0. So the absolute value of x plus 3 equals 0. And I really can't divide this up into a positive 0 and a negative 0. I just want to know where is x plus 3 equal to 0, and that happens where at x equals negative 3. Here we have one solution. So we can have all these different combinations, all these different possibilities when we're trying to solve, when we're trying to find a solution to an absolute value equality. Of course, the question then comes, what if I'm looking for an absolute value inequality? In other words, graphing on the number line. So if I have a situation where I've got g of x equals the absolute value of b times x minus h is less than or equal to c, the first thing that I want to do is find boundary points. In other words, I want to find out where is g of x, my absolute value, actually equal to c. And keep in mind that I'm going to have 0 or 1 or 2 solutions as we just did. But this is our first step. The second thing that we're going to do is we're going to test interior points. By solutions to determine truth. In other words, when I find my solutions, I'm going to have some solution happening here at P and some solution is going to happen here at Q. I need to test some number here, I need to test some number here, and I need to test some number here in my original inequality. And the idea is that testing and finding out yes it is true or no it's not true, that's going to allow me to write my intervals or inequality solutions. In other words, once I know something's happening, once I know that it's true for this and it's false for this and it's true for this, then I can say it goes from negative infinity to P or from Q to infinity. And I can write those as inequalities if I need to. I could have a situation where it's equal. In a situation where this has an equality in it, I could include those boundary points. But these are the 3 steps that I need to do, so I'm going to go through a few examples of this. So again, some examples. Let's say I want to solve the inequality absolute value of 3x minus 5 is greater than or equal to 16. So the first thing I need to do is I need to find my boundary points. In other words, where 3x minus 5 equals 16 or 3x minus 5 is equal to a negative 16. So here adding 5 to 16 gives me 3x equals 21 or x equals 7. That's one of my boundary points. Here adding 5 to a negative 16 gives me 3x equals negative 11, and so x equals negative 11 thirds. And so these are the boundaries that I need to test. So I've got negative 11 thirds and I've got 7. And I need to test a number in each of these intervals and determine if my inequality is true or false. If it's true or false for one value, then it's going to be true or false for every value in that interval. The easiest one to test, of course, is going to be testing x equals 0. If I substitute a 0 in for x, I'm going to have the absolute value of 3 times 0 minus 5. And I want to know, is this greater than or equal to 16? Well, this is the absolute value of negative 5 is greater than or equal to 16, which is not true. So if I'm not true, I know that this interval can't be part of my solution. I need a number that's bigger than 7, so let's test x equals 10, see how that works. So I got the absolute value of 3 times 10 minus 5. And I want to know, is this bigger than or equal to 16? Well, 3 times 10 is 30, minus 5 is 25. Is 25 greater than or equal to 16? Well, yeah, it is. And so because this is true, I know that from 7 to infinity is going to be part of my solution. So I need to test the number in this interval as well. Negative 11 thirds is just a little bit over negative 12 thirds, which would be x equals negative 4. So let's try negative 4. If I have the absolute value of 3 times negative 4 and subtract 5 from that, do I get something that is bigger than 16? Well, 3 times negative 4 is negative 12, minus 5 is negative 17, and the absolute value is 17. And I know that 17 is bigger than 16. So the interval from negative infinity to negative 11 thirds also satisfies the inequality. So my solution is going to be this interval or this interval. In other words, x is less than a negative 11 thirds or equal to, or x is greater than or equal to 7. And I can write it using interval notation. I can write it using inequality notation. Both are perfectly acceptable. I want to do another example of this. So let's take a look at the absolute value of 3/4 x minus 9. And I want to know when is this greater than 11? So again, step 1 is to find our boundary points. In other words, find out where it's equal to or where it's equal to the opposite of 11. So doing that, adding 11 to 9 gives me 20. 3/4 x equals 20. And multiplying both sides by 4/3, I end up with x equals 80 over 3. Doing the same thing over here, negative 11 adding 9 gives me a negative 2. So 3/4 x equals negative 2. And multiplying by 4/3 gives me x equals negative 16 thirds. So what I need to do now is, actually negative 16, negative 8. My goodness, I'm doing horrible tonight. So for my interval, I'm going to be testing negative 8 thirds, and I'm going to be testing 80 thirds. So again, let's try x equals 0. That's the easiest number to substitute. Substituting a number here in 0, 0 minus 9 is negative 9. 9 greater than 11? No, that's not true. So this is not going to be part of my interval. I need a number that's smaller than negative 8 thirds, and negative 9 thirds would work, so negative 3. So if I have 3/4 of negative 3 minus 9, and I want to know, is this greater than 11? Well, 3/4 of that's going to give me negative 9/4. And if I have a negative 9 and I dig 9/4 deeper down, that's going to be negative 11 1/4. And that is bigger than 11 when I take the absolute value off. So this works, and the interval for x being less than negative 8 thirds is part of my solution. Now I need a number that's bigger than 80 thirds. Let me try 81 thirds, which is 27. So if I take 3/4 of 27 and then subtract 9, I want to know, is this bigger than 11? Well, 3 times 27 is 81. 81 divided by 4 would be, well, 80 divided by 4 is 20. So that would be 20 1/4. Minus 9 is going to be 11 1/4, which is greater than 11, and that works. So x is greater than 80 thirds, certainly is part of my solution as well. And of course, I could write these using interval notation if I wanted to, but inequalities are perfectly acceptable. I want to do one last example here. So let's take a look at a situation like negative 2 times the absolute value of x minus 9 plus 4 is greater than negative 3. So in a situation like this, I'm going to try and isolate this because I need to get this by itself to figure out what my boundary points are. So the first thing I'm going to do is subtract 4 from each side. I get negative 2 times the absolute value of x minus 9 is going to be greater than negative 7. And then divide both sides by -2. That's going to give me x minus 9 is going to be less than 3.5. And of course, keep in mind, because I'm dividing or multiplying by a negative number, that changes my inequality. That's something I need to remember from algebra. And so now to find my boundary points, I want to find out where this is equal. So x minus 9 equals 3.5, or x minus 9 equals negative 3.5. And I can either add to give me 12.5, or I can subtract, which is going to give me negative 9 and negative 3.5. That's 9 and 3.5 is 5.5, so 5.5. Keep in mind, though, that I really do have this as part of my truth that I need to consider. I really do have a situation where absolute value must be greater than 0. So I need to consider x equals 9 as part of my boundary situation. And in reality, it's equality, so we can actually include this point if we need to. So this can be an endpoint if I need to. So looking at my number line, I have 3 boundaries that I need to look at: 5.5, 9, and 12.5. And I need to choose a number in each interval to test. And of course, I've mentioned several times, but 0 is the easiest number to substitute. Substituting in here, 0 minus 9 is negative 9. That becomes a positive 9 times 2 is negative 18. Negative 18 plus 4 is negative 14. And this does not work, because negative 14 is not bigger than negative 3. Testing a number in here, I could do x equals 7. 7 works good. 7 minus 9 is going to give me a 2. Negative 2 times 2 is 4. That's going to be a negative 4 plus 4 is 0. And 0 is larger than a negative number, so this works. So I know that from 5.5 to 9 is going to be part of my solution. Let's test another number over here. Let's try 10. So 10 minus 9 is 1. That's going to give me a negative 2 times 1, which is negative 2. Plus 4 gives me a positive 2, which works. So my interval has to include 9 to 12.5. And if I try a number bigger than 12.5, let's try 20. 20 minus 9 is 11. That's going to give me a negative 22. A negative 22 plus 4 is a negative 18. And that is not bigger, so this is not going to work. So I've got this or this, but in reality, because 9 is a shared endpoint, I really can kind of smush it together and say it starts here and ends here. And of course, I've got parentheses on there. I could say that x has to lie strictly between 5.5 and 12.5. Absolute values are tricky to deal with, mainly because we have a concept of equality, but we've got this nebulous aspect where my sign is kind of ignored. It's equal to x when it's positive, it's equal to negative x when it's negative. So it's a little difficult to work these problems out, which is why we need the practice of going through how to graph these, how to look at them from finding the solutions of an equation, how to find the solutions of inequalities. These are all important things to know. Once again, this is Mr. Potter. Thank you for watching. Have a great day.